Hello everybody, welcome back. So let's continue talking about the photoelectric effect. In particular, let's talk about how the photon model of light explains all the observations we talked about in the previous video. So in the photon model, what we have is, instead of viewing this light that's hitting this emitter that you see on the right there as a continuous wave, we're going to consider this to be a bunch of photons. So let me draw a photon coming in. I'll redraw it like this. That's a little cluttered. Here's our emitter, here's our collector. We're going to have a photon coming in. Now here's the whole key to how we can explain these observations. An electron that's bound to this metal here, it can only interact with one photon at a time. That's what we're going to say. So it can absorb energy from just one photon. Now, it takes a certain amount of energy for that electron to break its bonds. That's what we're going to call the work function. And it's traditional to use a phi for this work function. Even the name work function, it's an old name. Really, it's a binding energy, but the idea of it being the amount of work that has to be done to liberate the electron is why we call it the work function. So every metal is going to have a characteristic work function. It is an energy. So every metal has a characteristic work function, the energy that has to be absorbed by the electron in order to be liberated. Okay, so this photon has some energy E sub pH. So this electron, which can only interact with one photon, it's going to absorb this energy from the photon, all of it, right? It can't just absorb a little bit. It's going to take all the photon energy. So the difference between the photon energy and this work function, whatever's left over, can be used to make a getaway, can be used as escape kinetic energy. Now, some of this difference in energy might be lost in a collision. So this difference is going to be the maximum kinetic energy, big K max, that one of these liberated photoelectrons can have. Right? So the maximum kinetic energy is when all of the energy from the photon minus the work function, all of that energy difference goes into the kinetic energy. Okay? All right. So if we remember that the energy of a photon, and I'm going to rearrange this equation like this, because that's how I want to write it. So if we remember that the energy of the photon is HF, I have this equation. Right? So right away, though, we can see that there has to be a cutoff frequency, right? Because if this energy of the photon is not sufficient, if it's not greater than the work function, this electron is not going to be able to be liberated. It won't be able to break its bonds. So realizing the photon energy is directly proportional to the frequency, we know that there's a cutoff frequency. We can figure that out right away. I'm going to call that F sub CO. In fact, the cutoff frequency has to be such that it is the energy of the photon, H times that cutoff frequency, has to equal exactly the work function, right? If the energy of the photon is less than H times F sub cutoff, you're not going to liberate the electron. So in fact, we can figure out that the cutoff frequency for a particular metal is going to be the work function, the binding energy of the electron for that metal, divided by Planck's constant. So there you go right there. All right, we have that. Okay, so we have the idea of the cutoff now already. And if you remember, I'm going back to those quantum physics study questions. For observation 1, for frequencies below a certain cutoff frequency, no photoelectrons are seen. Well, now we have the explanation from the photon model. You can see it right here. Since electrons interact with one photon at a time, the one photon must have a sufficient energy equal to the work function in the material to eject the electron. The energy of the photon is HF, so there is a minimum frequency. Okay. Let's see. Oh, this idea of the photon, one photon interacting with one electron, also explains observation 2. What's observation 2? The stopping potential, and therefore the maximum kinetic energy of a photoelectron, is independent of light intensity. If we keep the frequency the same, right? But if we crank up the light intensity, in the photon model, what we're doing is we're increasing the number of photons per time that are hitting the metal. But since one electron interacts with one photon at a time, the energy of that one photon, right, that's what determines the maximum kinetic energy. It's not the number of photons that are hitting the metal per time. It's just the energy of a single photon. If you don't change the frequency, you're not changing that. So increasing the intensity, the number of photons per time hitting the metal, is not going to change that stopping potential. So that explains that observation. Now, what about this observation? A plot of stopping potential versus frequency is linear. Well, let's go back to the equation that I have written right here. Okay? And let's remember that the maximum kinetic energy is equal to the fundamental charge times the stopping potential. So fundamental charge E times V sub S is equal to HF minus phi. Let's just divide by the fundamental charge. So now we have this equation. I'll put this in parentheses. So Planck's constant over fundamental charge times frequency minus work function phi over fundamental charge. This is what we get from considering the photon model. Now, if I ask you to plot V sub S on the vertical and frequency F on the horizontal, you look at that equation, that's a line. That's slope-intercept form, right? That's y equals mx plus b. Look at this equation right here. In fact, according to this boxed equation, the slope of this line up here, this slope m, should be Planck's constant over fundamental charge. Ha! In fact, here is an experimental way, another way to actually evaluate Planck's constant. So, in addition to what Planck did with thermal radiation, where he was first introduced the constant, here's an independent way to get at Planck's constant. And sure enough, when you do an experiment like this with the photoelectric effect, you get a value of Planck's constant that is the same with an experimental error of what you get from thermal radiation. Okay, and to continue this, you can get at the work function of the metal by looking at making this plot right here. The work function, right, is going to be given by that vertical intercept. So if you extend this down, if you extend this line down, right, dash, 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 that is predicted to be minus the work function of the metal over the fundamental charge. Again, the work function is going to be characteristic of what type of metal is this. Okay, so here's an experimental way to determine the work function of that metal. All right, so Photon Model explains this plot perfectly. And in fact, not only explains that you get a line, but also shows you that you can get at Planck's constant and the work function of the metal by analyzing the plot. Cool. Now, the last observation, remember, was photoelectrons are emitted in a very short time, even in very low light intensities. That makes perfect sense because since one electron interacts with one photon, it takes just one photon to eject an electron. So even in very low light levels, where you're sending just a few electrons per unit time, you're still going to be ejecting photoelectrons because it's one photon that's being absorbed. So all four of these observations now are explained by the photon model of light. In addition, let me go back to the summary notes. In addition, we have a way to determine Planck's constant with this equation right here. and the work function of the material, remembering that the stopping potential is that maximum kinetic energy over the fundamental charge. Okay? So, wow, this was a really successful explanation of what was observed. And if you've read about Einstein, you may have read that he is the one that did this photoelectric effect work with the photon model. And this was part of the reason, part of the work that he did when he got the Nobel Prize. It was an incredible couple of years for Einstein. He did work in this, also in what's called Brownian motion, and also on relativity theory around the same time. So they gave him a Nobel Prize for all of that work that he was doing. Photoelectric effect analysis was part of it. Okay, so that's the photoelectric effect explained by the photon model of light. Okay, what we're going to do so make sure you know how to manipulate these equations, but also know right here, right, in your quantum physics study questions, know what is the photoelectric effect and know how to explain these observations using the photon model. Okay, that's it for this video. What we're going to do in the next video is we'll look at an application of the photoelectric effect, which is the, I'm sorry, I should have mentioned that the equations in this video that we covered that you're responsible for also continue on the next page of the study notes. That's where we summarized the idea of the cutoff frequency and wavelength. Oh, I guess I should mention the wavelength. Okay, let me do that. Let me just finish by saying in the next video, we're going to go and talk about the PMT, the photomultiplier tube. But let me just make sure you guys see where this cutoff wavelength is coming out. So let me go back here. So we have the idea of the cutoff frequency right here, box right here. Now remember, the photon energy, right, is HF, but we can also write it as HC over the free space wavelength. Okay, or we can write it as, right, that combination HC is 1243 eV nanometers over lambda naught. So there is a cutoff wavelength that is associated with this cutoff frequency. Okay, and all you have to do is put in for the F the cutoff frequency, which is phi over h. Right. So when the photon energy is the work function, by definition, that's going to give you the cutoff wavelength. So I'll call that lambda sub CO. Right. So you can find the cutoff wavelength by knowing the work function, just using this. And that's what you see right here in the summary notes. Okay. The cutoff wavelength is HC over the work function. All right. And also realize though, right, you need a frequency greater than the cutoff frequency to produce photoelectrons. So that means you need a shorter wavelength. Because remember, when wavelength goes down, photon energy goes up. Frequency goes up, photon energy goes up. Okay. All right. So next video, we'll talk about the PMT. Bye-bye.